All right, Unit 6 review, trigonometry. Number 1, a farmer has a triangle field ABC shown in the diagram. They give us that length AB, or you could call it side C, is 35 meters. BC is 80 meters, and angle BAC, or at angle A, is 105 meters. They also tell us that D is the midpoint of BC. So even before I start looking at my actual question, I can remember that that means BD is 40 as well as DC is 40 in case I need that later. For part A, we're asked to find the size of angle BCA. So we're looking for angle C. So because looking at the whole triangle ABC, I have angle A and side A. And I'm looking for angle B given side C. That means I'll use the sine rule for this one. All right, so I've set up my sine rule with side A over sine of angle A, side C over sine of angle C. When I cross multiply and isolate sine C to look for that angle, I'll be looking at 35 sine 105 divided by 80. So I'll type that into my calculator and do the inverse sine of it since I'm looking for an angle. And I'll get that angle C, or angle BCA, how they called it in the problem, is 24.998 from my calculator or from Desmos, but to 3 sig figs, I would have 25.0 degrees. Part B, we're calculating the length of AD. So from A to that midpoint of D that they gave us before. So remember, now I already know that B to D is 40 meters, and also D to C, just writing that in now that it's appropriate. So if I'm calculating the length from A to D, so I'm going to call that also side B since it's now across from angle B. I have two sides, and I can also easily find this missing angle. Remember, we just found angle C. So if I subtract 105 minus the, if I subtract 180 minus 105 minus the 25 I just got, I know that angle B is 50 degrees. So while I can't use the 105 at all, just because I'm not exactly sure how this gets cut from this line, I at least know that I have a side angle side triangle. So I don't have any connecting piece like I did in part A, so I can't use the sine rule. I'll have to use the cosine rule instead. So setting up my cosine rule, if I'm looking for side B or side AD, I will have my two sides squared and added together. So 40 squared plus 35 squared minus 2 times those two sides times the cosine of the angle I'm given, which is 50 degrees. So again, this formula is given to you in the formula booklet. It's just you have to know how to manipulate it for the problem or the sides and stuff that you're given. So when I put that into my calculator and take the square root, I get 32.0186, which to three significant figures, I'll look at 32.0 meters. Part C, the farmer wants to build a fence around ABD, and we're calculating the total length of that fence. So we know now ABD. So we already knew A to B was 35. We derived that A to D is 40, and we just found A to D being 32. So we just have to add all three up to find the total length. And that'll get me 107 meters, 107 meters. Part D, the farmer wants to build a fence around ABD. So that's why we had to find the total length of the fence. We already knew that, sorry. The farmer pays $802.50 for the fence, and we're trying to find the cost per meter. So if he pays a total of $802.50, And we know the total meterage was 105. Oh, I'm sorry, 107. Then we'll just divide them to figure out the total cost per meter. So we're looking at around $7.50 per meter. Remember, you're talking dollars and cents here, plus this is 3 significant figures as well, but we should have that zero at the end. Part E, calculating the area of triangle ABD. So remember our area formula. In our area formula, the letters don't necessarily matter. You just need a side angle side triangle. So you need the two sides with the angle between them. So looking back at our diagram, we're looking at ABD, so not the whole thing, but just that smaller triangle we've been focusing on. We have had almost from the beginning our side angle side triangle. So I can use that 35 with the angle of 50 with the other side of 40, side, angle, and side. So subbing into my formula, going to my calculator or to Desmos, I'm getting 536.2311. So that means to 3 sig figs, I'm looking at 536 square meters. And finally, part F, a layer of 3 centimeter thick is removed from ABD for finding the volume removed in cubic meters. So a couple of different things to point out here. Number one, especially the older IB problems love to sneak in these conversions. So make sure, especially on reviews, that you look out for them. We try to, especially on assessments, bold them for you. But in the reviews, we sometimes miss the bolding. So first up is I'm going to convert this centimeters into meters since my area was in meters and they want the final volume in cubic meters. So if I want to convert 3 centimeters into meters, handy to know that 1 meter is equal to 100 centimeters. So conversion trick, whatever you want to convert into, make sure there will be one left, meaning that in this case, how I set this up, my centimeters units themselves will cancel out. So that's why I put the centimeters on the bottom. So if you're ever not sure, do I multiply to get a big number? Do I divide to get a small number? That's how you can work on like kind of setting it up. Also, just kind of think about the direction you're going in. We're going from a small measurement into a larger measurement. So therefore, this small number will have to get smaller when I convert it. So if I multiply straight across, I can leave it as 3/100, or I think in general, most of us are more comfortable with decimals. So I can say 0.03 meters. So that's just converting the 3 centimeters into meters. Part 2 of this is remembering that finding the volume, you can just do the cross-section area multiplied by the height. So whatever area of the piece that you're looking at multiplied by the height. So we just found the area. We'll just take that 536 multiplied by the 0.3. And so during our area of the cross-section, 536 times our height, or the thickness, in our case, now converted to the 0.03, I'm looking at 16.08, or to 3 sig figs, 16.1 cubic centimeters. All right, number 2, we have this archaeological site. They give us all the information both in the setup and in the diagram. So we're looking for part A, the distance from A to C. So we're looking for this dashed line distance. I'm going to call it B just because it's across from angle B. So I do not have, and I cannot easily find a matching pair. The only angle I have is angle B, and that's the side I'm looking for. So that tells me I'm looking at the cosine rule. So setting it up, since I'm looking for angle or side B, I'm going to use the B squared formula, kind of mirroring the C squared formula from your formula booklet. You have one side squared added to the other side squared minus 2 times each of those sides. Times the cosine of the angle between them. So putting that in a calculator or into Desmos and taking the square root, I'm looking at 387.01527, or to 3 sig figs, just 387 meters. Just a note for both number 1 and number 2, your calculator or your Desmos should be in degrees. Anytime they give you the angle in degrees, that's what mode you should be in. All right, letter B, we have that same beginning diagram on the bottom, if you notice, but now they added point D. So the archaeologists are planning to build 2 more straight paths from A to D and then D to C for the paths to go around the site. Angle BAD is to be made 85 degrees, and BCD on the other side is 70 degrees as shown on our new diagram. I'm going to go ahead and transfer our 387 that we just found to this diagram though, because A to C isn't going to change at all. That's what we just found. In part B, what they're really asking us to do is to find the angle of size BAC. So BAC, so that means we're looking at this smaller angle. So I'm going to label it B for part B. So focusing on, kind of trying to ignore that top triangle, focusing on what we have down here, we have angle B is not changed at all. We know this side from A to B is 185. We know this side from B to C is 250, and we know side A to C is 387. We do not know angle C over here. We know that that big angle C is 70 degrees, but we don't know inside this little triangle what that is yet. So when I'm going to find this smaller angle over here, I'm going to have to use the, or I can use the sine rule this time, sorry, because I have I have angle B with the side across from it. So we can use sine rule for this one. All right, so I went and set up my sine rule, side B over the sine of angle B, side A, which is that 250, since it's still across from the angle I'm looking at, divided by sine of, I'm just going to keep calling it angle A. You could also call it angle BAC. Cross multiplying and solving for that sine of the angle we're looking for. I'm looking at 250 sine 125 divided by 387. So in my calculator, I'll want to do the inverse sine of that fraction. And when I do that, I get 31.949, or to 3 sig figs, 31.9. Part C, finding angle CAD. So C to A to D, that means I'm looking for now this angle. So remember, we just found the angle below it as 31.9. So that means to find angle CAD, all I'm doing is 85, since we know that's the big angle A, subtracting that 31.9 that we just got. So we're looking at 53.1. Part D, finding the size of angle ACD. A to C to D means I'm looking for this angle at the top. So what we can do is kind of the same thing that we did between parts B and C, is find the piece on the bottom first within the triangle that we know more about, triangle ABC, and then subtract what we get from 70 degrees. So I'll use the sine rule first to find this angle. And then I'll subtract what I get from 70. All right, so using the sine rule again to find angle ACB first, this little dotted angle. I set it up using the B information, still using the 385 with the sine of 125, but this time setting it equal to 185 since that's across from that small angle I'm looking for, divided by the sine of C. So again, cross multiplying, isolating sine C, and then doing the inverse sine of that in my calculator, I'm getting 23.05311, etc. Using part 2, using that 70-degree angle, since we know that's the giant angle C, and subtracting what we just got from it will give us the angle that they actually asked for. So I would get 46.946, etc. So to 3 sig figs, we're looking at 46.9 degrees. All right, and finally in part E, they're telling us that the length of path AD is 287. So we now know this length is 287. And we're asked to find the area of region A, B, C, D, so the whole plot. So we have plenty of information now to find the area of angle or of triangle ABC. And now that they gave us that piece, we have a side angle side triangle in ACD in this top triangle because we had already found this pink angle A, and we have the two sides that surround it. So it's going to be another 2 parts, finding the area of ABC and then finding the area of ACD and adding them together. All right, so my area of ABC I chose to use the angle 125, which was angle B with the 2 sides that surrounded it. And when I do the math in my calculator in Desmos, I get 18,942.89, etc. For angle ACD, again, using that small angle A of 53.1 with the 387 and the 287, I get 44,410.08, etc. So adding those together gets me the total plot, which is around 63,352.978, etc. So to 3 sig figs, we would be looking at around 63,400 square meters. Remember, at least 3 sig figs. If you have more than that, then that's fine, but at least 3 sig figs. In number 3, a surveyor has to collect the area of the triangular piece of land DCE, so this bottom triangular area. C to E can't be measured directly because they go through a swamp, and they tell us that AB at the top, DE at the bottom, BD and AE are all straight paths, and that DB and AE intersect right at point C. So just explaining the diagram that they give us that we know it's not drawn to scale. And they also give us all the measurements that are also shown in the diagram. First up, we're asked to find the size of angle ACB. So A to C to B, so that's this one. So looking at that triangle ABC, we're given all 3 sides, no angles at all, so that automatically tells me I can use cosine rule. This time I'm looking for an angle, luckily it's angle C. In the formula booklet, I say luckily because it gives you cosine of C equals, so I can just fill in my sides accordingly. So side A is 10 squared plus side B is 12 squared minus side C of 15 squared divided by 2 times 10 times 12. Doing the inverse cosine of that ginormous fraction, I get that angle C or angle ACB is 85.459, or to 3 sig figs, 85.5 degrees. Part B, show that the size of angle DCE is 85.5, correct to 1 decimal place. So angle DCE, which is this one. Note that it's the exact same thing we just got, right? So instead of showing, I'm going to more explain. If you think back to geometry, vertical angles are opposite angles when two lines intersect. So because angle ACB and angle DCE are opposite angles from two intersecting lines, that automatically means that they're the same. So any kind of explanation about vertical angles can show that angle DCE should be 85.5. Part B, the surveyor measures angle CDE to be twice that of DCE. So both of which are focusing on this bottom triangle. So angle CDE, this one, is measured to be twice that of DEC, of this triangle. So that means whatever this is twice of that, or 2 times that. So I'm going to use angle E to be just X, which means that angle D would be 2X, twice of that angle. So if we're also using the fact that DCE up here in purple was 85.5, we're going to find angle DEC. So we're going to use that information to find angle DEC. We're trying to find this angle. All right, so not necessarily using sine rule or cosine rule. If you notice, they gave us a lot of information about the 3 angles within this triangle. So we know that all 3 of those angles, the 2x, the x, and the 85.5, all have to add up to 180. So we'll just write ourselves a little formula for it and then solve for x, which will get us the angle they're asking for. So combining like terms, and also at the same time, I'm going to go ahead and subtract that 85.5 from the 180 to get the 3x by itself, so 94.5. And then dividing both sides by 3. So we're getting that x equals, or angle DEC equals 31.5. Part 2 of part B, finding the length of D to E. So finding this long length, I'm just going to call it D to E. Getting a little messy here. So looking at what we have, we now have angle E being 31.5. We also have the angle, or the side across from it, being 9. We were given that in the original problem. We have angle C at the top, which is across from DE. So that means I can use the sine rule for this one. So setting up with my sine rule, and then cross multiplying and isolating for DE. In my calculator is going to go 9 times the sine of 85.5 divided by the sine of 31.5. Notice that this time we're finding a side, so we don't have to do the inverse sine at all. We're just going to throw this into our calculator or into Desmos to get our answer. So we're looking at 17.178. But to 3 sig figs, we're looking at 17.2 kilometers. Finally, part 3, calculating the area of DEC. So calculating the area of this bottom triangle. That was the whole goal throughout all of this anyway. If you remember from the beginning, they have to calculate the area of that triangular piece. So that's why we've had to do all this work. So thinking about the area formula, remember you need a side angle side triangle. So you need the angle with the two sides that surround it. So looking at the triangle and the angles that we have DE, or sorry, angle E now, and we just found side DE, but we don't have this other side from C to E. Same predicament with angle C at the top, we have side C to D, but we don't have side CE. And finally, the one angle that we do have the two sides for, we don't have that actual angle. So it's really just kind of picking your poison. Do you want to find angle or side CE using sine rule again to be able to use the 85.5 or 31.5? Or do you want to find angle D just by doubling angle E? Because remember we said that this angle, angle D, is twice that of angle E. To me, that's the easier option because you just have to double it or multiply it by 2. And then you can just use that with the 9 and with the 17.2 that we got. So that's what I'm going to do is I'm going to first double that angle E that we had gotten before. So I'm going to calculate, or I'm going to find angle CDE just by multiplying that 31.5 by 2. So I'm getting 63. And then in step 2, actually using my area formula to find the area. So 1/2 times the two sides that surrounded it, which was 9 that was given to us, and the 17.2 that we just found, times the sine of the angle between them, which is that 63 degrees. So I'm looking at 68.963, which means to 3 sig figs, I'm looking at 69.0 kilometers squared. You should get the same answer if you choose to find that missing side instead and use one of the other two angles. All right, number 4, into circles. We have a circle here with radius of 40. Points A, B, C are on the circumference, and AOC, this angle, is 1.9 radians. So very important to note that we're in radians here. So in terms of the formulas we'll be using, we're going to have to use the formulas for arc length and for area for when your angle is given to you in radians. So that means right off the bat, finding my arc length in radians, the length equals just the radius times the measurement of the angle. So I'm looking at 40 times 1.9, or 76 centimeters. So definitely look out for how your angle is measured because it's going to change which formula you use. Part B, when I'm finding the perimeter of the sector. So we just found this length of the sector itself, the arc length. Perimeter of that whole sector, though, means I'm going to also have to add these 2 radii to that 76 that I just got. So the 76 from the arc length plus the 2 radii, which hopefully I remember from geometry or before geometry that it's the same length. And I get 156 centimeters. Part C, finding the area of sector OABC. So finding the area of this piece. If I'm in radians, my area equals 1/2 r squared theta. So I'm looking at 1/2 times my radius, which is 40 squared, times theta, which is 1.9. So I'm looking at 1,520 centimeters squared. All right, and number 5, note that this is a different problem. We're asked to, in 5A, find the area of this shaded region of the circle of radius 10 centimeters. So note that they're only giving you the sector here, right? Even though we know it's part of a whole circle since they said it in the problem. So in order to find just that shaded region, I'm going to have to do two things. I'm going to have to first find the area of the sector. And then two, I'm going to have to find the area of the triangle ABC. When I go to find the area of the sector, make note that we are in degrees this time. They say that this angle A is measured at 70 degrees. So when I go to find my area of the sector, I'll be using the formula that states that the angle is measured in the degrees. So I'll have the angle itself, 70, divided by 360 times pi r squared. Oh, but my r is 10. They told me that my radius was 10. So 10 squared. And I'll get whatever I get. When I go to find my area of the triangle ABC. So remember, if this is part of a whole circle, if A to B is 10 for my radius, A to C is also 10 centimeters. So again, I have a side angle side triangle. So I'll use that same area formula we were using before, 1/2 times the two sides times the sine of the angle between them. Just make note that you do have to be in degree mode for this since the angle was given to us in degrees. All right, so my area of the sector, after going to my calculator, I'm getting around 61. In my area of the triangle, I'm getting around 46.98. So if I'm trying to find just that small shaded section, I'm subtracting the two, the area of the bigger one minus the area of the smaller one, and I'm getting 3 sig figs now, 14.1 squared centimeters. Again, do not round until the very end. Wait until that very last step before you round to 3 sig figs. For 5b, we're asked to find the area of the shaded region of the circle of radius 10. So they actually didn't write that in the diagram this time, but they did again show us that this central given angle at angle F is measured in degrees at 70 degrees. So this diagram is pretty bad. For all intents and purposes, let's assume that they are basically taking out this sector GCF. We're going to say that this is a sector. If you see it as a triangle, it's going to minorly change your answer, but it is going to be a different answer. So for all intents and purposes, I'm going to say this is a sector versus a straight across triangle, just because it's hard to see if it's a straight across triangle, is there any shaded piece then in that little piece there? So if this was a test question, I mean, it wouldn't be a test question because it's a horrible diagram. So if it was a test question, though, we would be very explicit with what it looks like. So let's pretend it's a sector. So two different ways that you could solve this problem then. You could, option one, which is the option I'm going to go with, you could remember that full circle is 360. And then you could do 360 minus 70 to get this piece on the outside, or the central angle of the shaded piece. So I'm looking at that angle being 290 degrees. And then use that in that area of a sector formula, given that your angle is measured in degrees. You could also, in case you don't remember that, or in case maybe it's in radians and you don't remember that a full circle in radians is 2 pi, you could also find the area of the whole circle and then subtract out just the area of the sector. Either way, it'll get you the same answer. I'm going to roll with this way just because it was a little bit faster, since especially I already found my angle measurement. So I'm looking at that 290 divided by 360 times pi r squared, which my radius again is 10. So I would be looking at, to 3 sig figs, 253 centimeters squared. Number 6, we have this circle with center O and radius 3. And once again, they're telling us that that angle is measured in radians. For part A, we're asked to find the length of the arc ABC. So finding this length. Again, I'm in radians, so my formula is just the radius times that central angle. So 3 times 1.3 to get me 3.9. Part B, finding the area or the perimeter, of the shaded region. So we're finding the perimeter of the shaded region. So one thing to note, perimeter, hopefully, especially after number 4, we have to remember that it includes these radii, right? Those 2 3s. But we also have to realize they're looking for the shaded region. So the perimeter of this large Pac-Man kind of circle. Finding that shaded region, we can, I think probably the best option would be to find the circumference of the whole circle and then subtract out that arc length ABC that we had already found. That'll get me that outer edge that we'll then have to add the 2 3s to. So I'm going to find my circumference first. And circumference formula, it doesn't matter if you're in degrees or radians, it's still 2 pi r. Or in our case, 2 pi times 3. I'm going to leave it for now as 6 pi, just so that I don't round too early. Remember, we don't want to round prematurely until right at the end. So that was step 1. Step 2, I'm going to find the whole perimeter. So I'm going to find first the area of the the length of the shaded arc. So taking that 6 pi minus that 3.9 that we had just gotten. And then to that, whatever that is, I will add my 2 radii. When I do that, I get 20.949, or to 3 sig figs, just 20.9 centimeters. Part C, finding the area now of the shaded region. So finding the area of Miss or Mr. Pac-Man here. So again, very similar to number 5. If you remember that your full circle is 2 pi, you can do 2 pi minus 1.3 and use that difference with your area formula or your area of a sector formula in radians. You can also find the area of the full circle, subtracting out the area of this unshaded region. It's really your choice. It just kind of depends on which one you feel more comfortable with. Do you remember that the full circle is 2 pi in order to find this arc length or this central angle measurement? I'm going to go with finding the area of the circle. And then subtracting out the area of the unshaded sector. All right, so my area of the circle formula, again, doesn't matter if you're in degrees or radians, it's still just pi r squared. Subbing in my 3 for my radius, I get 9 pi. Again, trying to not round too early. When I find my area of the not shaded sector, using my formula when my angle measurement is given to me in radians, I have 1/2 r, or 3 squared times 1.3, which gets me around 5.85. And then just subtracting those two, 9 pi minus 5.85 gets me to 3 sig figs now, or correct to 3 sig figs, 22.4 square centimeters. All right, question number 7, the depth of water in a port modeled by the function p cosine qt plus 7.5. for T being between 0 and 12 inclusive, where T is the number of hours after high tide. Before I even get into the rest of this, I'm going to remember that cosine, the graph of cosine, is that upside down, or not upside down, it's the U shape. So it starts at a maximum and then kind of follows through the repetition. Getting back to the given problem, though, at high tide, the depth is 9.7 meters. At low tide, which is 7 hours later, the depth is 5.3 meters. And we're first asked to find P, which if you notice where P is in the formula, P is looking for the amplitude, or the A. They're going to mix up the numbers on you, or the letters on you all the time, so make sure you just know where they are in the formula. So if I'm looking for the A, that information they gave me before will be helpful as well. So high tide, my depth is 9.7. My low tide, the depth is 5.3. So if you remember, finding the amplitude, we can do our max of the Y value minus the min Y value and divide it by 2. So you're just finding the average of the max and the mins. Sorry, not the average, but the difference, half the difference of the max and the min. We're trying to find out the distance from that midline to the max or to the min. So if I do 9.7, sorry, minus 5.3 divided by 2, I'm looking at 2.2 as the value of P. Part B, we're asked to find the value of Q. So note that they don't specify whether this should be in degrees or radians. So we would accept either in degrees or in radians. It doesn't matter. And I'm bringing that up because Q, if you notice, is the piece in front of T. So that's equivalent to our B value, which can be found by remembering that the period equals either in radians 2 pi over B or in degrees as 360 over B. And so either way, whether you're in degrees or radians, I'm going to go with radians just because I'll give you the answer, the final answer in degrees as well, but I'm going to stick with radians for now. Either one you choose, though, you need to know what the period is, right? So if you recall that the period there's a lot of different ways that we can find it, but one way, which especially for the given information that we have, one way is to take the horizontal distance from the max to the min and double it. So doing 2 times the max x, oops, minus the max min. Oh, sorry, the min x. All right, so let me restate that. To find your period, you're finding the difference, the horizontal difference between the max and the min, and you're doubling it. One thing to note, though, and I started to do the parentheses here, it's always going to be positive. So we might even want to say that we're doing the absolute value of this. So I'm saying that, and you're probably thinking, well, I don't have an x value at all here. However, they did say that at high tide, which is a max, the depth is 9.7. I know that's the y value, but that means that this maximum point was at 9.7. At low tide, which is 7 hours later, the depth was at 7 or 5.3 meters. So that means my min point, if you will, would be at 5.3. So that means my x and my my x from my max and my x from my min, I'm looking at 2 times the x from the max, which was 0, minus the x from the min, which is 7. So it's really just a difference of 7, right? Remembering that it's the absolute value. So 2 times 7 gets me 14 as the period. Again, not my final answer. That's just the period. I need to use that in step 2 to find my b value. So again, I'm going to go with radians. So saying my period, or setting my period equal to that 2 pi over b. Cross multiplying and simplifying. I say that because I'm going to leave my answer in exact terms or in terms of pi, so pi over 7. If you're doing it in degrees instead, and setting that 14 equal to 360 divided by b, cross multiplying and solving, you'll get that b equals 180 over 7. Oops, not 188, 180 over 7. And even though I know this is our final answer for part B, I'm looking ahead and it says use the model that you found. So remember, we just found the missing pieces in this model. We found the P and we found the T. So we're going to be using that model to find something else. So that's why I'm going to leave it like this. If you rounded here, we would accept that as well. If you gave us whatever the decimal equivalent is to 3 significant figures, we would accept that as well. All right, so getting to that, using that model. So bringing all the pieces together before I even continue, my model was d of t equaling p, which we found first to be our amplitude of 2.2, times the cosine of, and this is where things might differentiate depending on whether you used radian mode or degree mode. I'm going to run through it all in radian, and then I'll explain in degrees. So in radian mode, I have my b, which in the formula they gave us was q. So pi over 7 times t plus the 7.5 they gave us. So we're finding the depth of the water, which is our d, 10 hours after high tide. So that means my t equals 10. So I'm just using this formula and subbing in 10 for t. Make note, though, that if you are in degree or in radians, right? I use that pi over 7 for radians. That means that when I do this in my calculator or in Desmos, I'm going to need to be in radian mode. So I can type this whole thing into Desmos or into my calculator, making sure I'm in radian mode, and I get to 3 significant figures, 7.01 meters. Right, so alternatively in degrees, my setup would be still the 2.2. That didn't matter whether I was in degrees or radians, but cosine of 180 divided by 7t plus 7.5. So same idea that I would sub in 10 for t. And then go to my calculator. But remember, I would have to be in degree mode for this because my b, depending on my period, which I measured in degrees for this one. Oops, 5. So I'll still get the same answer. It's just a matter of whether you use degrees or radians. That's what mode you need to be in. And finally, number 8, our diagram shows the graph of a sine bx plus c. Again, kind of switching our numbers here. Usually that plus at the end is a d in the formulas that we've been using previously. So just make sure you're paying attention. They also tell us that x is measured between 0 and 12, again, inclusive. They give us a graph this time, though. The graph has a minimum point at 3.5. Go ahead and label that. And a maximum point at 9.17. And we're first asked to find the value of c. Again, the same thing as our D, or our vertical shift, remembering that it's basically just averaging the y values of the max and min. So max y plus min y divided by 2. So I'll take my 5 plus my 17, I just went in the opposite order, it doesn't matter, divided by 2. And I'll get 11. Part B showing, part 2 showing that B equals pi over 6. So note that they are talking about B, which is the piece that's being multiplied to x, so it depends on my period. And note that they're saying that it equals pi over 6. That usually indicates that we're talking in radian mode. Anytime you're seeing a B here, or a period, or an angle measurement, when they give you a pi, that means they're talking in radian mode. So we're going to do kind of the same thing that we did in number 7, that we'll first have to figure out the period. And then we'll use that to find the B. Like, they're giving it to us, which is nice. But we'll just still show the same steps as if we didn't have the answer. It's just now that we can check our answer at the end. So finding my period, again, we're looking at horizontal distance this time. Scoot it back up. So I'm looking at twice, or 2 times, the horizontal distance between the max and the min. So the max, keep myself consistent with number 7, the max x minus the min x. Horizontal or absolute value, because we cannot have a negative distance. So we're just kind of checking ourselves with that. So my max x value is 9, minus my min x value is 3. So that means the difference between them is 6, times 2 is 12. Not my answer, so I'm not going to box it yet. That's just my period. Part 2, remembering that my period equals in degree, or in radians, 2 pi over my B value. That means I'm looking at 12, the period I just got, equaling 2 pi over B. Cross multiplying, and I'll show this work this time, cross multiplying, I get 12b equaling 2 pi, and dividing by 12. Simplifying, because I have 2 over 12, I would get 1 pi over 6, or pi over 6. So, I mean, you can box it up, but again, that's not the point. The point with this was the show. So showing that you know how to get all of this, and you're just being able to check your answer at the end. Finally, part 3 here, finding the value of A. If we go back up to the top, A is what it normally is. It's the amplitude. So remember, the amplitude, you're finding the vertical distance between that axis of symmetry, or the vertical shift that we found earlier, to the maximum, or that distance from the principal axis to the minimum. Either way, you're finding, you can think of it that way. You can add in that principal axis that we had already found at 11. If you can draw a straighter line than I can. But knowing that it's at 11, and then finding that difference up to the maximum, the y value of the maximum, or down to the minimum. That's just getting you your amplitude. You can also, if you aren't sure, if you're C, the value that we got in part 1, if you're ever not sure that it's correct, remember, you can find the difference between the min y values and then divide them by 2. So I'm going to show that latter piece just in case. I'd rather show the longer way. So the max y minus the min y divided by 2, which means I'd be looking at 17 minus 5 divided by 2. So I'd be looking at 6. However, I tried to differentiate between the amplitude and the A. Remember, the absolute value of A does equal your amplitude. However, with this problem, remember, sine itself normally, its parent function looks like this. So it always starts at 0, 0 and goes up before it decreases. Versus this one, it does start on the y-axis. Obviously, it's been shifted. We already talked about that for part 1. But now that it goes down first, it decreases first. That means the a value itself is going to have to be negative. So just writing out kind of what I was just saying. But the key is that my final answer for part 3 is that a should be a -6.